Hello ladies and gentlemen, welcome back to GGS 300, Quantitative Methods for Spatial Science. Today we've got the 10th laboratory session, and that's going to be the laboratory session which accompanies the lecture which hopefully you've just watched, which was on correlation. So that was lecture 13. We've got some data here from the Lattice package, so I'm going to install it and just load it into the environment, load it into the global environment here. You can just download this code. It should be on Blackboard now for you. So download it and open it up the normal way that you do for the previous laboratory sessions. So you can just get the .r script, open it up here, and if you've already got Lattice, you won't need this package installed here. But I'm just running it for you because I don't know if we've used Lattice so far this term. So you can see down here in the output, it's actually just said it's spat out a whole load of lines of code from basically it actually going to the R CRAN, so the server where you can download R packages, and then it's installed it, and it said that it successfully unpacked and successfully passed a variety of checks. And now once we've got that, we can just click require Lattice. This just means that it's been imported now into the environment we currently have open, and we're able to go to the environmental data. So this is a data set, and basically allocate it to a data frame. And when we actually open that, we can see that we've got these 4 columns: ozone, radiation, temperature, and wind. Okay, so why don't we take a look at what this data is. And if you do that, you can go look at the documentation for this data that's being recorded here, and we have the daily measurements of ozone concentration, wind speed, temperature, and solar radiation in New York City from May to September 1973. So obviously it's quite old. Usually these are kind of seminal data sets that people have collected, which have widespread acknowledgement of them being somewhat useful, but also kind of small in size. So they can be passed around. They're used as demonstrators for the code functionality that comes with certain packages. And obviously New York City is kind of renowned for those hot, very humid summers, here we're particularly talking about things like ozone issues. And actually I think it's going to give us a bit of an overview of what they are. So when we talk about ozone, we're talking about the average concentration of hourly measurements in parts per billion. And when we're talking about temperature, we're talking about the daily temperature in degrees Fahrenheit. Okay, so if you want more information on this, then you can go off and have a look. Obviously, those sorts of air pollution issues that come about are particularly heightened when it gets hot, because for example, in New York City, London also, those very tall buildings and the fact that you have so much dense urban environment means that you get these canyons between the buildings, and it means that the air pollution gathers there and it can't just be blown off. And particularly added into that, the kind of New York City humidity in the summer, it means that it causes a lot of environmental problems. It causes a lot of health issues. A lot of people die early as a result of that level of air pollution exposure, unfortunately. So this is something to be aware of. We've got this very simple data set, and now we can do what we really want to do here, which is get into some of those correlation assessments that we covered within the lecture. So enough about the data set. So we can take 2 columns that we're interested in. So here let's take temperature and let's take ozone, and let's have a look at the relationships between the 2 of them. Okay, so we can allocate these as arrays into the global environment in R, and then we can actually plot these. So we can plot the temperature against the ozone. Here we have its degrees Fahrenheit on the x-axis, and the parts per, sorry, let me just get that correct. It's the ozone concentration in parts per billion on the y-axis here. And you can kind of see a slightly positive correlation between the 2, but it's kind of weak. But it becomes particularly elevated down here. Once you get to very high temperatures, the ozone starts to shoot up. So I imagine that this is the really hot days, hot sticky days in NYC, when the pollution also starts to get really challenging, particularly if you've got no wind, no doubt. Okay, so what we want to do is we want to do Pearson's R. So I'm assuming that you all covered this this content within the lecture. So you'll remember that we first calculate the covariance between two different metrics, x and y here. And then when we've got that, we can basically get this R here. So the covariation divided by the number of paired data values divided by the standard deviation of x and y multiplied together. So to do that, we first need to get the covariance. So here we need to get the mean first. So for each of these x bar and xy, we know that because in here we're going to need the standard deviations, we need to get those metrics too, so we can just use the inbuilt standard deviation function. So we've got that for the mean and now the standard deviation, and we've just placed them into the global environment up here in the right hand corner. And we can just get the length of just a single variable is fine because they're the same length. And that's going to give us the total number of paired data points that we have, which is 111. And then once we've got that, the first thing we can do is get the covariation of x and y. So to do that, we can subtract the mean from each one of the data points and multiply them together and then get the sums. So this is going to be the deviations for each one of those variables. And then when we do that, we're getting a covariance here of about 24,367. And then that's fairly straightforward to calculate. We can then enter into this little simple nifty equation that we've got here, which is fairly straightforward. So the covariance divided by the number of paired data points that we've got divided by, and it's the multiplication of the standard deviation for x and y. And then when we do that, we end up with 0.69, so it's a correlation of 0.69, which is relatively strong positive correlation, okay? But what we want to be able to do is to actually formally test this. So we want to actually just run through that little test statistic equation so we can get the required t. So here what we're doing is we're going to take the r value that we've already got, multiply it by the square root of the number of degrees of freedom divided by the square root of 1 minus r squared, okay? So that should be fairly straightforward. We've got our numerator here, and we've got our denominator here for these two numbers, which we just saw from the previous equation. And when we do that, we get a t-value of 10.01, so it's quite substantial. It's quite large. And then we can actually use our standard function. So this is for the student t-distribution, but we can get the p-value, so the probability value of the occurrence of that particular value by using this standard function, which now you must have used many times because you've had lots of assessments in order to submit, so you must have worked out how to use this function, so I'm not going to spend much more time on it. But we get a very, very highly significant p-value, and it's very, very small, so it's 1.97 to 10 to the minus 17. So it's incredibly small, highly significant, and what this is saying is that there is a significant relationship here between these two variables, okay? So that was the manual way for us to actually produce it. There are other ways in which we can produce those correlations. So if we go help core here, this is actually producing the documentation for the inbuilt functions, which allow us just to kind of do this automatically. So now you know how it's done. You won't have to do this in too much detail. You can basically just run this particular function with the two variables that you want to look at the correlation for, and the r that you get is 0.69. Okay, so that's just matching up with the 0.69 that we got manually when we ran through that code up there in a more kind of laborious way. Okay, so let's move on now. What we want to do is to calculate the rho to see whether or not there is a correlation between x and y. So this is just literally repeating what we've already done basically, but it's giving us a more formalized way to actually test what we found up there. That gave us a reasonably similar answer, but not exactly similar. But this is a formalized way for us to check the correlation and actually test these two variables. So we got a highly significant p-value again. It's not exactly the same, but it's very, very similar. So that gives us a quicker way to obtain that result, basically. As we covered within the lecture, obviously this is kind of for a parametric based approach. We may need to carry out a non-parametric based approach if, for example, we don't meet those assumptions that we covered already within the lecture and which are in the book. They're also in the lecture slides. So if we don't have the ability to say that we meet all of these, then basically we would need to look at Spearman's rank correlation coefficient. So we're able to basically convert that data into ordinal observations. And then when we've got that, we can just run through this pretty much as kind of similar logic to how we did in the previous example. Okay, so you can actually use the core function again. So this is incredibly handy. You notice that we've looked at the correlation, we've looked at the correlation test, using just this single set of functions from within the statistical toolbox, which R has. The difference is that we're able to specify the type of method, for example, that we want to actually use. So what this is saying is you need to input as your arguments an x variable and a y variable. So they're the two factors we want to look at the correlation for. You can specify what you use. So you can specify whether you want to remove NA values, so values which don't have any data points, or whether you just use everything. And then you can state the method, so whether it's Pearson, so that's for your parametric based approach, Pearson correlation coefficient, or whether for the non-parametric based approach you just want to use the Spearman's rank. So that's exactly what we're doing here. That's why this method m value equals, and if you can actually just input s for the method Spearman. Okay, when we do that, we find we actually get an even stronger correlation once we downgrade that data to ordinal. So it's a positive correlation, 0.77 is quite strong. So we can also test the row to see whether or not there is a correlation between x and y. And we're using the Spearman's rank approach here. So again, we've got very, very significant findings. So this is suggesting that we have significant evidence to reject the null hypothesis and accept the alternative hypothesis that these two variables are in fact correlated, and there is a significant relationship there. Okay, and it gives you the rho value as well as the p-value. Okay, and then you're also able to, if you want to, you can run these for particular one-tailed directional tests. So previously we were just saying that we think there's a relationship as the alternative hypothesis. We weren't saying whether it's larger or whether it's smaller, but you can actually specify whether the alternative is greater or less than. So you can actually capture that within the relatively straightforward formulae that we've been using already. So that was kind of the content which we covered mainly in lecture 13. Hopefully now we can move on to just picking up a couple of those things which we didn't really pick up from the previous lecture. So I think I said it was the previous lecture in the lecture that we just had. Actually, it was 2 lectures ago, because we had inferential spatial statistics last week. But so we're picking up those categorical tests which we missed out a couple of weeks ago, and we're just going to run through some of them here so that we know exactly what was going on. And one of those important ones was actually being able to test data to see whether it's normally distributed or not. So we used the Kolmogorov-Smirnov goodness of fit test, and essentially that's telling us whether we think the data that we've got actually meets that assumption of normality, which is just so fundamental to all of those parametric tests that we've covered this term. Okay, so I think I mentioned before that it's somewhat laborious, burdensome to calculate the Kolmogorov-Smirnov test because we have to do this cumulative assessment. Instead, what we actually do is the Shapiro-Wilks test, which I quoted the function for in the previous lecture, and which we can just apply now. So we actually have these two different data variables. So we have the temperature and the ozone. We can actually test the temperature using the Shapiro-Wilks test. When we do that, we get 0.09. So it's not actually a significant result, which means that we can't say with certainty, at least at the 95% level, that the data are not normally distributed. And as a consequence, we can continue in this case with a parametric-based approach if we want. And actually, when we just graph the data that we have here for the histogram, we can see that it's kind of borderline, but it's kind of at least part of the graph is looking quite normally distributed. I think the lower part of the tail looks a little bit out of shape, but obviously this test is indicating that it's not significantly different from normality, and therefore we can proceed if we would like to. On the other hand, if we actually look at the ozone data, what we notice here is that we have really quite significant p-value. It's incredibly small, 2.84 to 10 to the minus 8. So it's really quite significant and therefore different from the normal distribution. So if we found this result, it meant that we wouldn't be able to continue with our parametric-based approaches for assessment. We'd have to look at carrying out non-parametric-based tests. Now, here we have the ozone data plotted, and you can see that this is nowhere near normally distributed. It's incredibly positively skewed, so you have a really long tail over here. This obviously does not conform to that normally distributed data requirements that we have. Okay, so if you need more information on this, then you can just look at lecture 11. It contains pretty much everything that you need to know. Obviously, we have these two different hypotheses here. If it's not significant, then distribution is normal. If we have a significant result, then basically the distribution is not normal. Okay, so that's the way that we need to think of this. And then just finally moving on now. So I think we've just got two more tests left, the chi-squared, which we'll run through quickly now, and then contingency analysis. So it shouldn't be too arduous for you. The goodness of fit tests that we cover help to see if the sampled frequency counts that we get are similar to the expected frequency counts. So there's plenty of this within the actual lecture, so we kind of covered this, that we might go out and collect some data, and then we're interested in knowing, okay, does the categorical data which we collected, which we've observed, actually conform to maybe what we just would expect to occur by random or not? So how much does the data that we've got actually deviate from what's expected? Okay, and we can do this in a variety of ways, whether it's focusing on uniformly distributed data, proportionally distributed, or normally distributed data. What we need to do is to actually get the chi-squared test statistic in order to make this assessment. So we need to get the expected frequency count, subtract it from the observed frequency count, square it to get those the sum of the squared deviations. And then we need to divide it by the EI expected frequency count that we have here, and then we need to sum across all of those nominal ordinal categories that we have for all the different categories in our data set. Okay, so let me show you very simply what we do here with this. So hopefully you know the test already now, but we just have this very simple example. So imagine we want to check if the expected number of people that actually commute to school, to college, to the university by certain methods is similar to what we actually sampled. So in this case, we asked geography majors if they either walk, they take a bus, or if they drive to a school. And the results are that essentially 10 people walk to school, 10 people take a bus, and 40 people drive. Okay, so the question is this uniform? And we can first put this data, so let's just clear the global environment, put this data, these geography students, the results of this geography student assessment into the global environment here. Once we've got that, it's very easy for us to start to get some of these metrics. So we want the expected frequency count, we want to know the number of categories that we've got. So if we do this, we basically take the mean across all of these counts here to give us our expected value, which is 20. So that's the mean number of people that we would expect for any one category based on the survey that we've carried out. Then what we need to do is we need to subtract the EI from the O and square. So that's what we're doing here in this part of the equation. So we're subtracting the expected from each one of the geography variable results that we got, and then we're squaring them. Okay, and then we just divide again by the expected number, and then we sum them all in order to get this chi-squared test statistic. Okay, so when we do that, we get 30. So it's not necessarily a particularly large number, but let's put this now into our function, which helps us get the probability for this particular outcome. And that function that we're using here is the chi-squared package from the R-stat package. Okay, so this is the non-central chi-squared distribution. And this should be fairly similar to you now. So we have the ability to query the density, the probability, as we will do in this case, quantile, or just generate a random number from a chi-squared distribution. Okay, so these are all specific to this one type of chi-squared distribution. When we do that with our chi-squared, we get a very significant p-value. So this is 3.05 times 10 to the minus 7. So this is definitely a significant finding, which indicates that we have enough information at the 95% level in order to reject the null hypothesis and accept the alternative hypothesis. Okay, so we were interested originally in understanding how many people actually took a certain method to school. Okay, so what we're doing here is we're basically saying that the results that we've got are significantly different from what would occur just at random, essentially. Okay, so that's how we kind of crunch through the numbers manually. Hopefully you're able to understand this relatively simple equation for how we got the chi-squared test statistic. I think the key point is that if you actually need to carry out this chi-squared test, you can do it relatively easily within R. So if you've got that geography vector of the 3 different outcomes, you can actually just use the chi-squared.test, which should hopefully produce something relatively similar. So we end up with a very similar p-value of 3.05 times 10 to the minus 7. For that particular result. Okay, so that should mean that you can reproduce that answer in just a cheeky one-liner in R, in case you need to do that in the future. So let's finish. We've just got this one final test to do now, and then I can let you go and you can get on with the assessments or re-go over the lab materials, whatever you want to do in order to improve your existing knowledge on this topic. So within that final part of, I think it was lecture 11, we basically went over contingency analysis. So this is what happens when we have multiple, so for example, 2 categorical variables that we're interested in. We're interested in comparing the observed frequency against an expected frequency distribution, okay? So let's see if there's a difference between the transportation mode which people actually use to get to GMU and the major which they actually take. So in other words, do we actually see a difference between the majors which people take? So although we've got the geography numbers above, we can actually take samples from chemistry and also math majors and use those data points that we collect within this particular example. So for chemistry students, 30 walk to GMU, 20 take the bus, and 50 drive. Whereas for math students, you have 20 walking, 20 taking the bus, and 40 driving. So read into that what you will about subjects. Okay, let's add that data into the global environment now. So we have the chemistry, geography, and math students up here for their different transportation modes. We can then create a data frame out of that. So we have this transportation data set here. And the way to think about this, if you like, if it's easier, is to think of the data frame as a matrix. So for each of those transportation modes, we have the numbers and the modes being across the rows, and then the the actual subject majors being the columns across here. Okay. Now what we need to do in order to get that cross tabulation is we need to get the expected frequency count for the ith row and the jth column, so we need to be iterating across the whole matrix, and we need to get the observed number as well, and then we need to square them, and we need to divide it by the EIJ, so the expected frequency count for the ith row and the jth column, and we need to do this across all of the different rows and columns that are in our data set. Okay, so let's get stuck in. We need to first take the number of total rows and total columns, so I think it should be fairly easy for us to do that. There's 3 in each because it's just a very small matrix that we put together. We do need to get the marginal sum, so this is just basically saying what's the row sum and what's the column sum, and if you've not actually encountered the apply function before, you can have a look at it here. It's quite a handy function to use, and what it's doing is just saying for this data set transportation, I want you to apply this method, and here 1 refers to the this margin variable, which is just basically saying which dimension of the matrix do you want to sum across in this case. So if it's 1, then that's indicating we want to sum across the rows, and then if it's 2, then that's indicating that we want to sum down the columns, basically. Okay, and then the function is just whatever function we want it to be, and here we've just gone for the simplest because that's what we need, so it's just a sum function. So that should be relatively straightforward for you, and when we place those into the actual memory, we get the row sums and the row columns for each one of those different dimensions. Okay, so you can see it up here, 60, 180 for the column sums, and for the row sums we get 60, 50 and 130. Great, so what's the total number of data pairs that we've got? And for n that's 240. Oh sorry, not data pairs, that's the total row sum. Okay, so the total n overall. So hopefully that's fairly straightforward for you. And then all we need to do just to finish this off is we can actually do it in a handy matrix multiplication. So we can use the outer function that we have inbuilt within R, and we can just provide 2 different matrices and allow it to basically sum along each one of those entities within the matrices. So that's basically us iterating across each ith row and each jth column. Okay, so let me think if we can now do this. Let's produce the expected outcome, so that's taking into account all row sums and row columns divided by n, and we get our expected amounts here, and it's in exactly the same dimensions as the actual data which we've got, which is handy because in the next piece we just need to finish off our equation here. So for each of these matrices, so we have the transportation, so these are our observed results, we have the expected data, so this is what we would expect to just randomly occur, and then we can subtract the expected from each transportation data point, square it, divide it by the expected value again, and then sum that, and what we end up is the chi-squared statistic that we're interested in for this particular example. Then we just need to get the number of degrees of freedom before we progress, so when we do that we get 4. So we're subtracting 1 from the number of rows and 1 from the number of columns and multiplying them together. And then when we go back to that same chi-squared distribution that we used previously, we want p chi-squared because that's indicating we want the probability for the occurrence of this chi-squared test statistic here. When we do that, we get 0.18. So we don't get a significant finding in this particular case, which basically means that we don't have enough information to reject the null hypothesis, which means we retain the null hypothesis, and that we don't see any difference across majors in terms of the transportation patterns. Okay. You can, of course, just run this sneaky one-liner, this chi-squared.test down here. So you can use the help menu if you want to take a bit more of a look into what that function does, but we just have to provide it with the actual data that we've got, transportation, and then we open up the Pearson chi-squared test results here for the transportation data set. So we get chi-squared of 6.4 1744, so very similar to that number that we got before. There's always a little bit of rounding error depending between how you carry it out manually and the result that you actually get. And then that's sometimes complicated a little bit more when you use non-parametric results and you get the ties in the rankings and you have to deal with them. But here we basically provided the number of degrees of freedom. We got the p-value of 0.18665. Here it's been rounded, but it's basically exactly the same as the one we got manually. Great, so I'm hoping that wasn't too overloading for you. You've got the materials for this week's lecture on correlation, so that was lecture 13, and you've got the materials for the lecture 2 weeks ago, which was lecture 11, and that should really kind of cover off all of those different tests that we've covered in the past couple of weeks, that we've covered in the lectures, but maybe we haven't covered fully in the laboratory sessions. So now really, once you've completed this week, and obviously that's your first task to complete the assignment that's been set, we really just have that one single assignment for you to complete on regression next week. And then once you've completed that, we just have the midterm, and then you're on to the sunlit uplands of the summer holidays. So I'm sure you'll be looking very much forward to that. Great, well, thanks for tuning in anyway. Do reach out to me if you've got any further questions. I'll look forward to hearing from you, and I hope you have a very good week. All the best. Goodbye. Thank you.